Scientists just found something that breaks every rule we know about planets. A world shaped like a lemon, with diamonds buried deep inside circling a dead star so fast it completes an entire year in just 8 hours. And here's what has astronomers stunned: this planet challenges everything we thought we knew. Stay with me. In the next few minutes, we're going to explore one of the most bizarre discoveries ever made in space. And by the end, you'll understand why this single finding is forcing scientists to rewrite everything they thought they knew about how planets survive in the universe. Imagine waking up one morning to find that gravity stopped working in your backyard. That's essentially what happened when researchers at the University of Chicago analyzed data from the James Webb Space Telescope and discovered a planet that challenges our current understanding of planetary formation and survival. This isn't some distant theoretical prediction or a computer simulation gone wrong. This is a real world, orbiting a real star, detected by the most powerful telescope humanity has ever built. And every single thing about it, from its shape to its composition to its location, tells us it has no right to be there. The discovery came quietly, the way most revolutionary findings do. Scientists were sifting through Webb's observations, looking at the faint infrared signatures of distant star systems, when they noticed something unusual around a pulsar designated PSR J2322-2650. Pulsars are already strange enough. They're the collapsed cores of dead stars, spinning faster than a helicopter rotor, compressed into spheres the size of a city. But orbiting this particular pulsar was something that made absolutely no sense. A planet. A massive planet. And not just any planet, but one twisted and deformed into a shape no one had ever seen before. The lead researchers' first reaction, documented in their published paper, was simple and direct. What the heck is this? That's not the kind of language you typically find in academic journals. Scientists are usually careful, measured, and diplomatic in their wording. But when you discover something that fundamentally contradicts your entire field of study, sometimes the only honest response is raw bewilderment. And that's exactly what this planet delivered. Bewilderment, confusion, a sense that the universe just pulled off a magic trick no one can explain. Let me paint you a picture of what they found. Somewhere out in the depths of space, there's a planet roughly the size of Jupiter. But instead of being round the way planets are supposed to be, it's been stretched and squeezed by gravity into the shape of a lemon, or a football, depending on how you look at it. The entire world has been deformed, pulled by forces so extreme that the planet itself has lost its spherical shape. And buried somewhere deep inside that distorted world, beneath layers of dense atmosphere and crushing pressure, scientists believe there's a core scientists believe is made of diamonds, not small diamonds, not scattered diamond fragments, potentially a massive core, possibly Earth-sized, composed of crystallized carbon compressed into the hardest material we know. This isn't science fiction. This isn't speculation based on shaky evidence. This is a peer-reviewed discovery, published in the Astrophysical Journal, one of the most respected scientific publications in astronomy. The data came from the James Webb Space Telescope, the same instrument that's been showing us galaxies from the dawn of time and analyzing the atmospheres of planets in other solar systems. Webb provides precise measurements confirmed by multiple methods. When it detects something, that something is real. But here's what makes this discovery genuinely unsettling for astronomers. This planet is orbiting its star so close and so fast that it completes an entire orbit in less time than you spend sleeping at night. Imagine going to bed, waking up, and realizing an entire year has passed on this world. That's the scale we're talking about, and the star it's orbiting isn't even a normal star anymore. It's a pulsar, a stellar corpse so dense that a teaspoon of its material would weigh as much as a mountain. Pulsars create extremely harsh environments. They spin at incredible speeds, shooting out beams of radiation like cosmic lighthouses. Planets don't survive near pulsars. The radiation would gradually erode atmospheres and surfaces over time through tidal forces. Yet here's this planet, not just surviving, but thriving in an environment that should have destroyed it long ago. It's like finding a delicate flower growing in the heart of a blast furnace. It's incredibly surprising. Every model, every simulation, every theory we have about planetary formation says this can't happen. But it did happen. The planet is there. Webb saw it. Scientists confirmed it. And now the entire astronomical community is scrambling to understand how. The implications ripple outward in every direction. If a planet can survive in conditions this extreme, what else is out there? How many other impossible worlds are orbiting dead stars hidden from our view until now? What does this tell us about the resilience of planets, about the diversity of worlds in our universe, about the limits or lack thereof of where planets can form and endure? These aren't small questions. These are the kinds of questions that reshape entire fields of study. And this is just the beginning. Webb has only been operational for a short time. It's still in the early stages of its mission, still pointing its golden mirrors at new corners of the universe, still peeling back the curtain on cosmic mysteries we didn't even know existed. If it found this planet, this impossible, diamond-filled, lemon-shaped world in its first wave of observations, what else is waiting to be discovered? What other rules are about to be broken? If the idea of a diamond-filled planet orbiting a dead star fascinates you as much as it does me, hit that like button. And drop a comment. I want to know what you think could survive on a world like this. Subscribe, because we're just beginning to uncover what Webb is finding out there, and you're not going to want to miss what comes next. Let me show you exactly what makes this planet so strange, starting with something you'd never expect its shape. If you've ever looked at a globe or a picture of Earth from space, you know what a planet is supposed to look like. Round, spherical, smooth. That's what gravity does. It pulls everything toward the center with equal force, creating a sphere. It's one of the most basic principles in planetary science. Every planet we've ever studied, from tiny Mercury to massive Jupiter, follows this rule. Even if they're not perfect spheres, some bulge slightly at the equator, because they're spinning, they're still fundamentally round. That's what planets do. Until now. The planet-orbiting pulsar I mentioned earlier looks nothing like that. If you could somehow travel there and view it from space, you wouldn't see a sphere. You'd see something that looks like it's been grabbed by invisible hands and stretched, squeezed, deformed. Scientists describe its shape as resembling a lemon or an American football, elongated on one axis, compressed on another. It's a planet that's been pulled out of shape by forces so powerful they've literally reshaped the entire world. Think about that for a moment. We're not talking about surface features here. Mountains and valleys can change a planet's appearance slightly, but the overall shape stays round. This is different. This is the entire planet, its crust, its interior, its core being distorted by gravity. Imagine taking a ball of clay and squeezing it between your palms. That's what's happening here, except the clay is a world roughly the size of Jupiter, and the hands are the gravitational forces from the pulsar it's orbiting. Jupiter is the largest planet in our solar system. It's so big you could fit over 1,300 Earths inside it. It's a gas giant, massive and imposing, with storms larger than our entire planet swirling through its atmosphere. Now imagine something that size being twisted into an entirely different shape. That's the scale of what we're dealing with. This isn't a small rocky planet being gently tugged by gravity. This is a giant world being fundamentally altered by the extreme environment it exists in. But here's what makes it even more remarkable. Despite being roughly Jupiter's size, this planet is significantly less massive. It's lighter, which means it's less dense, and that tells scientists something crucial about what it's made of. This isn't a rocky world like Earth or Mars. It's not a pure gas giant like Jupiter either. It's something in between, something unusual, with a composition that researchers are still trying to fully understand. The leading theory is that it's filled with carbon, lots and lots of carbon. In fact, the entire atmosphere might be composed of carbon compounds, soot-like particles floating through dense dark clouds. Imagine looking up at the sky on this planet. You wouldn't see blue like Earth's sky. You wouldn't see the swirling bands of colour you find on Jupiter. You'd see darkness, thick, heavy darkness, filled with carbon particles drifting like ash after a fire. The atmosphere would be dense, oppressive, a permanent twilight even if you were on the side facing the pulsar. Light would struggle to penetrate those clouds, and beneath those clouds, deeper inside the planet, the pressure would mount, carbon compressed by its own weight, carbon being squeezed by the gravity of the layers above it, carbon transforming slowly, inevitably, into something harder, something crystalline. Scientists believe that deep inside this world, perhaps thousands of miles below the surface, the pressure becomes so intense that carbon stops being carbon in the form we recognize. It becomes diamond, pure crystalline diamond. Not scattered gems you could pluck from the ground, but a layer, possibly a core of solid diamond stretching for potentially thousands of miles. It's one of the most extraordinary predictions ever made about a planet's interior, and it's based on solid physics, on what we know happens to carbon under extreme pressure, on experiments conducted here on Earth in laboratories that can recreate these conditions on a tiny scale. We've known for a long time that diamonds form under pressure. That's how they're created naturally on Earth, carbon buried deep underground, subjected to immense heat and pressure over millions of years, gradually transforming into the hardest natural material we know. But Earth's diamonds are small. Even the largest ones are measured in inches, maybe feet. What we're talking about here is something on an entirely different scale. A core that could dwarf our entire planet. A diamond so large it defies comprehension, and this planet isn't stationary. It's not peacefully orbiting some gentle, stable star. It's locked in a tight, fast orbit around a pulsar, a dead star that's spinning dozens of times per second, blasting radiation in all directions. The planet completes one full orbit in less time than it takes for a single day on Earth. Think about that. A year on this world lasts about 8 hours. You could watch the sun, or what passes for a sunrise, cross the sky, and set multiple times in a single Earth day. Time itself moves differently there, not because of some science fiction time dilation effect, but simply because the orbital mechanics are so extreme. The proximity to the pulsar is what's causing the deformation. Gravity doesn't pull evenly on this planet because one side is significantly closer to the pulsar than the other. The near side experiences a much stronger gravitational pull than the far side. This creates what astronomers call tidal forces, the same forces that create ocean tides on Earth, but amplified to a scale that can reshape entire worlds. The planet is being stretched toward the pulsar on one side and compressed on the other, creating that distinctive lemon shape. On Earth, we experience tiny tidal effects from the moon. The moon's gravity pulls on our oceans, creating high and low tides that shift by a few feet. It's gentle, predictable, barely noticeable unless you live near the coast. What this planet is experiencing is like comparing a gentle breeze to a hurricane. The tidal forces are so strong they're not just moving water, they're moving rock, gas, the entire structure of the planet. And somehow, despite these incredible stresses, the planet holds together. It doesn't fly apart, it doesn't disintegrate, it maintains its integrity, even while being perpetually squeezed and stretched by forces that would tear most worlds to pieces. The surface conditions, if you could even call it a surface, would be absolutely hostile. The radiation from the pulsar would be intense, constant, unrelenting. Any atmosphere that wasn't thick and protective would be stripped away in relatively short order. The temperature would fluctuate wildly depending on where you were on the planet and where it was in its rapid orbit. There would be no stable seasons, no predictable weather patterns, nothing that could support life as we understand it. This is a world of extremes, a planet pushed to the absolute limits of what planetary bodies can endure. Yet it's there, it exists, it's real, and that reality is what makes it so profoundly important. Because if a planet this strange, this deformed, this seemingly impossible can exist, then our understanding of planetary diversity is far more limited than we thought. We've been building models, running simulations, creating theories about where planets can form and what shapes they can take. And this single discovery suggests that we've been thinking too small, too conservatively, too bound by what we've seen in our own solar system. Now here's where things get even more interesting, because the shape is just the beginning of this planet's mysteries. Diamonds have fascinated humanity for thousands of years. They're symbols of wealth, beauty, permanence. We put them in rings, crowns, jewellery. We marvel at their clarity, their ability to catch light and scatter it into rainbows. But beyond their aesthetic appeal, diamonds are remarkable from a purely physical standpoint. They're the hardest naturally occurring material we know. They form only under conditions of extreme pressure and heat, deep beneath Earth's surface where the weight of miles of rock compresses carbon atoms into a crystal lattice so tight, so perfectly arranged, that it becomes nearly indestructible. On Earth, diamonds are rare. They form in the mantle dozens of miles below the surface and only reach us through volcanic eruptions that carry them upward. Even then, most diamonds are small, a few carats at most. Large diamonds are extraordinarily rare, which is why they're so valuable. The idea of a diamond the size of a mountain is pure fantasy here on Earth. Our planet simply doesn't have the conditions to create something like that. But out in space, the rules change. Pressure and heat can reach levels we can barely imagine. And on this lemon-shaped planet orbiting PSR J2322-2650, the conditions are perfect for creating diamonds on a scale that makes Earth's largest gems look like grains of sand. Let me walk you through how scientists believe this happens. The planet's atmosphere, as I mentioned, is thought to be rich in carbon. Not the carbon dioxide we breathe out, but more complex carbon compounds, soot-like particles, perhaps hydrocarbons, molecules that are common in the outer reaches of solar systems, where temperatures are low and chemistry is complex. These particles float through the planet's dense atmosphere like ash in the wind, creating those dark, oppressive clouds I described earlier. But atmospheres don't extend forever. As you descend deeper into a planet, pressure increases. The weight of all the gas and material above you presses down with greater and greater force. On Jupiter, this pressure eventually becomes so intense that hydrogen, normally a gas, is compressed into a liquid, and then deeper still into a metallic form that behaves like a conductor. Pressure transforms materials, changes their fundamental properties. And on this carbon-rich planet, pressure does something extraordinary. It transforms carbon into diamond. The transition wouldn't happen suddenly. There wouldn't be a clear boundary where carbon ends and diamond begins. Instead, as you descended through the planet's atmosphere into its deeper layers, you'd gradually encounter conditions where carbon atoms start bonding differently. The soot particles would begin to crystallize, first into small structures, then larger ones. The deeper you went, the more complete the transformation would become. Eventually, miles and miles below the visible atmosphere, you'd reach a depth where the pressure is so enormous that carbon exists only in its diamond form, pure, crystalline, compressed into the hardest substance in the universe. Scientists predict that this diamond layer could be staggeringly thick, not inches or feet, but potentially thousands of miles. It might form a shell deep inside the planet, or it might extend all the way to the core. The exact structure is still a matter of debate because we've never seen anything like this before. We can't exactly drill down and take samples. All we can do is use physics, chemistry, and our understanding of how materials behave under extreme conditions to make educated predictions. And every calculation, every model, points to the same conclusion. Models suggest diamonds likely exist deep inside. More diamonds than exist in all of Earth's jewelers combined, compressed into a volume so vast it could dwarf entire countries. Imagine if you could somehow extract even a tiny fraction of those diamonds. The entire global diamond market would collapse instantly. Diamonds would become as common as gravel, but of course that's pure fantasy. This planet is unimaginably far away, orbiting a hostile pulsar and protected by layers of dense atmosphere and crushing gravity. Even if we wanted to reach those diamonds, even if we had the technology to travel there, the environment would destroy any equipment long before it got close. This is a treasure vault sealed by the laws of physics themselves, but the diamond core raises fascinating questions beyond mere material wealth. Diamonds have unique properties. They conduct heat incredibly well. They're electrically insulating in their pure form, but can become conductive if they contain certain impurities. They're transparent to many wavelengths of light. A planet with a massive diamond core would behave differently than planets we're familiar with. Its internal heat flow would be affected. Its magnetic field, if it has one, might be shaped by the presence of all that crystalline carbon. Even its evolution over time, how it cools, how it responds to tidal stresses, would be influenced by having a core made of the hardest material in existence. And then there's the question of how it got there. Diamonds on Earth form over millions of years, gradually crystallizing as carbon is subjected to heat and pressure. But this planet has a violent history. It's orbiting a pulsar, which means the star it originally formed around exploded in a supernova, one of the most energetic events in the universe. Supernovae release more energy in a few seconds than our Sun will produce in its entire lifetime. They obliterate planets, strip away atmospheres, hurl material across light years of space. Yet somehow, this planet survived that cataclysm. Or perhaps it formed afterward, from the debris of the explosion, coalescing in the extreme environment near the newborn pulsar. Either scenario is mind-boggling. If the planet survived the supernova, it endured heat and radiation that should have vaporized it. If it formed afterward, it assembled itself in a region of space so hostile that planet formation shouldn't be possible. Both options stretch our understanding of planetary science to its limits. Both suggest that planets are far more resilient, far more adaptable than we ever gave them credit for. Some scientists have even speculated about what else might exist inside this planet. Carbon isn't the only element that can undergo dramatic transformations under pressure. Other elements in the planet's interior could be compressed into exotic forms, metallic hydrogen, for instance, or high-pressure ices that remain solid despite extreme temperatures. The interior of this world might be a layered structure, each shell composed of different materials, each responding to pressure in its own unique way. It's a planetary cross-section unlike anything we've seen before. And here's the truly haunting part. We're only seeing the tip of the iceberg. The diamond core is a prediction, based on theory and observation. We haven't directly detected it. We can't peer through the dense atmosphere and layers of the planet to confirm its existence. All we have is indirect evidence the planet's size, its mass, its composition as inferred from spectroscopic data. The diamonds are there, almost certainly, hidden beneath miles of hostile atmosphere waiting in the dark. But we can't see them. We can only imagine them, calculate their presence, dream about what they might look like. It's a reminder of how much remains unknown, even in an age of powerful telescopes and sophisticated instruments. We can detect planets across vast gulfs of space. We can analyze their atmospheres, measure their masses, track their orbits, but we can't touch them, we can't explore them. We can only observe from a distance and piece together the story from fragments of light and data. Now, if the diamond core and the lemon shape weren't strange enough, wait until you hear about the orbit itself, because that's where things get truly impossible. Time is a constant we rarely think about. A day is a day, a year is a year. The Earth spins on its axis, giving us day and night. It orbits the Sun, giving us seasons and years. These cycles are so regular, so predictable, that we've built our entire civilization around them. Calendars, clocks, schedules, all based on the assumption that time flows steadily and orbital mechanics are stable. But on the lemon-shaped planet orbiting PSR J2322-2650, time works very differently. A year there, one complete orbit around the pulsar takes about 8 hours. Less time than a full night's sleep, less time than a workday. You could wake up, eat breakfast, and by the time you finished lunch, an entire year would have passed on that distant world. It's a pace of orbital motion so rapid it defies intuition. To understand why this is so extraordinary, let's compare it to our own solar system. Earth takes a year to orbit the Sun because it's at a certain distance, roughly 93 million miles away. The farther a planet is from its star, the longer its orbit takes. Mercury, the closest planet to the Sun, orbits in just under 3 months. That's fast by our standards. But even Mercury's orbit is leisurely compared to what's happening around PSR J2322-2650. This planet is orbiting so close to the pulsar that the gravitational forces are extreme, the velocities are tremendous, and the entire system operates at a scale we have no analogy for in our own neighbourhood. Pulsars themselves are already strange beyond comprehension. They're what's left after a massive star explodes in a supernova. When a star much larger than our Sun reaches the end of its life, it runs out of fuel. The nuclear reactions that have been supporting it against gravity suddenly stop, and gravity wins. The star collapses inward in a fraction of a second, compressing a mass greater than the Sun into a sphere about the size of a city. 10 miles across, maybe 20, an object so dense that a single teaspoon of its material would weigh as much as a mountain. And it spins, fast. Pulsars rotate at speeds that are difficult to comprehend. Some spin dozens of times per second. Imagine a sphere the size of a city, with more mass than the Sun, rotating faster than a helicopter blade. The physics involved are extreme. The magnetic fields generated by these spinning neutron stars are among the strongest in the universe, and as the pulsar spins, it shoots out beams of radiation from its magnetic poles, like a cosmic lighthouse. If those beams happen to sweep across Earth, we detect them as pulses, hence the name pulsar. Orbiting a pulsar presents extreme challenges. The radiation alone would be lethal, not just visible light or heat, but high-energy particles, X-rays, gamma rays, the kind of radiation that tears through matter, ionizes atoms, destroys molecular bonds. Any planet orbiting close to a pulsar is bathed in this radiation constantly. There's no escape, no safe zone. The entire environment is hostile. And yet, there's a planet there, not just surviving but intact, stable, orbiting like clockwork, year after year, whipping around the pulsar in a tight ellipse that brings it closer than any planet should ever be to such a deadly object. The forces acting on this planet are immense. Gravitational forces stretching and compressing it into that lemon shape. Radiation pounding its atmosphere. Tidal forces creating internal stresses that should, by all rights, tear the planet apart. But it doesn't tear apart, it holds together. Somehow the planet's internal structure is strong enough to withstand these forces. The diamond core, perhaps, provides a kind of rigidity that prevents total disintegration. Or maybe the planet is constantly reshaping itself, flowing and deforming like a liquid but maintaining cohesion through sheer gravitational binding. We don't know for sure. What we do know is that the planet is there, defying every model we have that says planets shouldn't survive in such conditions. Astronomers have a term for the region around stars where planets are expected to exist. They call it the habitable zone, though that's a bit of a misnomer because it specifically refers to the range of distances where liquid water can exist on a planet's surface. But there are other zones too, regions where different types of planets can form and survive based on temperature, radiation and gravitational forces. Pulsars, by most accounts, don't have these zones, or rather, their zones are regions of destruction, too close, and a planet would be ripped apart by tidal forces or vaporized by radiation. Too far, and it wouldn't have survived the supernova that created the pulsar in the first place. This planet exists right on the edge of that impossible boundary. It's close enough that the tidal forces deform it dramatically, but not so close that it's disintegrating. It's exposed to intense radiation, but it has a thick enough atmosphere to absorb some of that energy. It's orbiting fast enough that relativistic effects, tiny changes in time and space, predicted by Einstein's theories, start to become measurable, but not so fast that the orbit is unstable. It's balanced on a knife's edge, existing in a regime where planets rarely survive. And this raises the most profound question of all. How did it get there? Planets don't typically form close to stars. They form farther out, where temperatures are cooler and material can coalesce without being blasted away by stellar radiation. Even hot Jupiter's gas giants that orbit close to their stars are thought to have formed farther out and then migrated inward over time, pulled by gravitational interactions with other planets or the protoplanetary disk. But migration near a pulsar is even more complicated. Pulsars don't have protoplanetary disks, at least not the kind that normal stars have. They're born in violent explosions. Any planets that existed before the supernova would likely be destroyed or flung out of the system entirely. So where did this planet come from? Did it somehow survive the supernova, clinging to its orbit through sheer luck and resilience? Did it form afterward, from the debris of the explosion, assembling itself in the harsh environment near the newborn pulsar? Or did it arrive later, a rogue planet captured by the pulsar's gravity, slowed and trapped in an orbit that would eventually deform it into the shape we see today? Each scenario has its own problems, its own implausibilities, yet one of them must be true, because the planet is there. Some researchers have suggested that the planet might be the remnant of a stellar companion, another star that was orbiting the original star before it went supernova. When the star exploded, this companion could have been stripped down, its outer layers blown away, leaving only a dense core that became the planet we see today. It's a dramatic origin story, one that involves cosmic violence on a scale hard to imagine. But it fits some of the observations. A former star would explain the planet's mass and density. It would explain how it survived the supernova, and it would explain why it's orbiting so close it was already there, part of a binary star system, when the explosion happened. But even this theory has gaps. If the planet is a stripped stellar core, what's it made of? Stellar cores are typically composed of heavy elements, iron, nickel, carbon fused together in the intense heat of nuclear reactions. That would align with the carbon-rich composition scientists are detecting. But it doesn't fully explain the diamond core prediction, or the lemon shape, or several other peculiarities of the planet's structure. There are pieces of the puzzle that still don't fit. What's clear is that no existing theory fully accounts for this planet. It's an outlier, an anomaly, a world that challenges our assumptions and forces us to expand our thinking, and that's what makes it so valuable scientifically. Anomalies are where breakthroughs happen. When you find something that doesn't fit your models, you have two choices: ignore it or use it to build better models. The scientific community is choosing the latter. Papers are being written, simulations are being run, new theories are being proposed, all because of this one impossible planet. And the researchers who discovered it, they're just as baffled as anyone else. Which brings us to what might be the most human part of this entire story, the moment when trained scientists looked at the data and said, "What the heck is this?" Science is often portrayed as cold, logical, unemotional. Researchers in white coats, staring at screens full of numbers, making careful, measured statements hedged with qualifications and uncertainties. And to some extent that's accurate. Science requires precision, rigor, skepticism, You can't just make wild claims without evidence. You have to test, verify, replicate. You have to be cautious. But scientists are still human, and when they encounter something truly unexpected, something that defies their training and experience, they react the way anyone would, with surprise, confusion, excitement, sometimes even a bit of frustration, because the universe just handed them a puzzle with pieces that don't seem to fit together. That's exactly what happened when the team at the University of Chicago analysed the data from the James Webb Space Telescope and confirmed what they were seeing around PSR J2322-2650, a planet, a massive planet, in an orbit that made no sense, with properties that contradicted every formation model they knew. The lead researcher's response, which made it into the published paper, was refreshingly honest. What the heck is this? You don't see that kind of language in academic journals very often. Scientific papers are usually dry, formal, filled with passive voice and technical jargon. Emotions are kept in check, but this discovery was so bizarre, so far outside the realm of expected findings, that it warranted a departure from convention. And in a way, that simple phrase, "What the heck is this?" captures the essence of scientific discovery better than any polished abstract ever could. Because that's what exploration is really about: encountering the unknown, finding things that don't fit, asking questions that don't have easy answers. The confusion wasn't just about one aspect of the planet, it was everything. The shape, the composition, the orbit, the survival, all of it together created a picture that didn't make sense according to established theories. Let's break down why each piece is so problematic. First, the orbit. Planets aren't supposed to exist around pulsars, period. When a massive star explodes in a supernova, the blast is powerful enough to obliterate anything nearby. Planets that were orbiting the star before the explosion should be vaporized, or at the very least, flung out of the system by the shockwave. The fact that a planet is there at all, orbiting so close to the pulsar, is a problem. It suggests either that the planet survived the supernova, which seems nearly impossible, or that it formed afterward, which presents its own set of challenges. Formation after the supernova is difficult because pulsars don't have the kind of material-rich disks that young stars have. When a star is born, it's surrounded by a disk of gas and dust left over from the cloud that formed it. Planets coalesce from that disk over millions of years, gradually sweeping up material and growing larger. But pulsars are post-supernova remnants. The explosion scatters most of the material into space. There might be some debris left in orbit, but nowhere near enough to build a Jupiter-sized planet. So how did this one form? No one has a satisfactory answer. Second, the shape. Tidal forces deforming planets isn't unheard of. We see it in our own solar system with moons orbiting close to gas giants. Jupiter's moon Io, for example, is constantly being squeezed and stretched by tidal forces, which generates internal heat and drives volcanic activity. But Io is a small moon. The forces deforming it are measurable but relatively modest. What's happening to this planet around the pulsar is on an entirely different scale. The deformation is so extreme that the planet has been reshaped from a sphere into a lemon. That level of tidal stress should, theoretically, tear the planet apart. There's a limit to how much stress a planetary body can withstand before it fragments. This planet seems to be exceeding that limit and surviving anyway. Third, the composition. A carbon-rich planet with a diamond core is theoretically possible, but it's not something we've ever observed before. Most planets we know are either rocky, like Earth and Mars, icy, like many moons in the outer solar system, or gas-dominated, like Jupiter and Saturn. A planet made primarily of carbon, with an atmosphere of soot and a core of diamond, is a completely different category. It raises questions about where such a planet could form, what kind of environment would produce that composition, and how it fits into our broader understanding of planetary diversity. And fourth, the survival. Even if you accept that the planet formed somehow, and even if you accept that it's being deformed by tidal forces, the radiation environment near a pulsar is lethal. Pulsars emit intense beams of high-energy particles. Any planet caught in those beams would be constantly bombarded. Over time, that radiation should strip away the planet's atmosphere, ionize its outer layers, and gradually erode the planet itself. The fact that this planet still has a thick atmosphere, that it's still intact after presumably millions or billions of years, suggests that something is protecting it. But what? Is the atmosphere so dense that it absorbs the radiation before it can penetrate deeply? Is the planet massive enough that it can replenish its atmosphere faster than the radiation strips it away? Or is there some other mechanism at play that we haven't thought of yet? Each of these problems is significant on its own. Together, they form a compounding mystery. Every answer you try to provide for one question creates new questions elsewhere. It's like a scientific Rubik's Cube solve one face, and you scramble the others. And that's why the researchers were so baffled. They weren't dealing with a single anomaly that could be explained away with a clever hypothesis. They were dealing with a cascade of anomalies, each one reinforcing the sense that this planet simply shouldn't exist. But it does exist. The data is clear. Webb detected the planet through multiple methods, confirming its presence beyond any reasonable doubt. The measurements of its mass, size, orbit, and atmospheric composition are all consistent. This isn't a false positive or an instrument error, it's real, and that reality is what makes the discovery so important. Because if this planet can exist, then our theories are incomplete. We're missing something. Some process, some mechanism, some aspect of planetary science that we haven't fully understood. The scientific community thrives on challenges like this. When faced with something that doesn't fit, researchers don't throw up their hands and give up. They dig deeper. They propose new hypotheses, run new simulations, look for additional data that might shed light on the mystery, and that's exactly what's happening now. Teams around the world are studying this planet, trying to understand its origin, its structure, its survival. Papers are being published proposing different formation scenarios. New observations are being planned to gather more detailed information about its atmosphere and interior. Some scientists have suggested that the planet might be the remnant of a brown dwarf, a failed star that never accumulated enough mass to ignite nuclear fusion. Brown dwarfs occupy a middle ground between planets and stars, and if one were in orbit around the original star, it could have survived the supernova and been stripped down to what we see today. Others have proposed that the planet formed from a second-generation disk, a ring of material that coalesced around the pulsar after the supernova, perhaps from the outer layers of the exploded star that didn't escape the system entirely. Each theory has merit. Each one explains some aspects of the planet while struggling with others. And that's the current state of the science, a collection of incomplete explanations, each one a piece of a larger puzzle that hasn't been fully assembled yet. It's messy, it's uncertain, and it's absolutely fascinating. Because this is how progress happens, not through clean, straightforward answers, but through grappling with complexity, refining ideas, and slowly building a more complete picture of the universe. And here's what makes this even more intriguing. Pulsars aren't common, but they're not rare either. There are thousands of known pulsars in our galaxy alone. If one of them has a planet this strange, how many others might be hiding around different pulsars waiting to be discovered? Are we looking at an isolated oddity, or the first example of a whole new class of worlds? To understand just how hostile and unusual the environment around pulsars really is, we need to take a closer look at what pulsars are and why they're considered death zones for planets. When you look up at the night sky and see stars twinkling, you're looking at the present-day universe in a relatively peaceful state. Stars shine steadily, converting hydrogen into helium through nuclear fusion, producing light and heat in a process that can continue for billions of years. Our own sun is about halfway through its life, and it will continue burning for another 5 billion years or so before it runs out of fuel. When it does, it will expand into a red giant, shed its outer layers, and leave behind a white dwarf, a dense, slowly cooling ember about the size of Earth. That's the fate of medium-sized stars like ours. But for stars much more massive than the Sun stars with 8, 10, 20 times the Sun's mass, the ending is far more violent. These stars live fast and die hard. They burn through their fuel much more quickly, and when they run out, they don't gently fade away. They explode. Supernova explosions are among the most energetic events in the universe, releasing in a few seconds more energy than the Sun will produce in its entire lifetime. The explosion is so bright it can briefly outshine an entire galaxy, and the shockwave from the blast ripples outward at a significant fraction of the speed of light, obliterating anything in its path. What's left behind after a supernova depends on the mass of the original star. If the core is massive enough, it collapses into a black hole, a region of space where gravity is so strong that not even light can escape. But if the core is slightly less massive, it becomes a neutron star. And neutron stars are, in their own way, just as strange as black holes. Imagine taking more than the entire mass of the Sun and compressing it into a sphere about the size of a city. The density is almost incomprehensible. A cubic centimetre of neutron star material about the size of a sugar cube would weigh as much as a mountain. If you could somehow bring a piece of a neutron star to Earth, it would fall straight through the ground, through the bedrock, through the mantle, all the way to the centre of the planet, because nothing on Earth is dense enough to support it. Neutron stars are made almost entirely of neutrons, hence the name. Under normal conditions, neutrons exist inside the nuclei of atoms, held together with protons by the strong nuclear force. But in a neutron star, the pressure is so extreme that atoms themselves are crushed. Electrons are forced into protons, creating neutrons, and those neutrons are packed together so tightly that the entire star is essentially one giant atomic nucleus. It's matter in a state that we can't replicate on Earth, governed by physics that operates at the very edge of our understanding. And then there's the rotation. When a star collapses, it conserves angular momentum. The same principle that causes a figure skater to spin faster when they pull their arms in applies to collapsing stars. As the core shrinks from something the size of a large planet to something the size of a city, its rotation speed increases dramatically. Neutron stars can spin dozens, even hundreds of times per second. Some of the fastest spinning pulsars complete a full rotation in just a few milliseconds. It's hard to even visualize something that massive spinning, that fast without flying apart. But neutron stars are held together by gravity so intense that nothing can escape. As they spin, neutron stars generate powerful magnetic fields trillions of times stronger than Earth's magnetic field. These fields channel particles from the star's surface and accelerate them to nearly the speed of light. The particles stream out from the magnetic poles in narrow beams, like searchlights, and as the star rotates, those beams sweep through space. If one of the beams happens to point toward Earth, we detect a pulse of radiation each time the beam sweeps past. That's what makes them pulsars. They're not actually pulsing, they're spinning, and we're seeing the lighthouse effect of their radiation beams. Now imagine trying to survive as a planet near one of these objects. The radiation alone would be catastrophic. Pulsars emit not just visible light, but X-rays, gamma rays, high-energy particles, all forms of radiation that are deeply destructive to matter. There's no atmosphere thick enough to fully shield against this bombardment. Over time, the radiation would strip away gases, ionize molecules, break down complex structures. Any life, any chemistry, anything delicate would be destroyed almost immediately. Then there are the tidal forces. Neutron stars are incredibly dense, which means their gravity is incredibly strong. But gravity weakens with distance, and if you're orbiting close to a neutron star, the difference in gravitational pull between the near side and far side of your planet becomes enormous. These tidal forces stretch objects. On Earth, the moon's gravity creates tides in our oceans, raising and lowering sea levels by a few feet. Near a neutron star, the same effect would stretch a planet by miles. Mountains would rise and fall like waves, the entire crust would flex and deform, and if the planet is close enough, the tidal forces would exceed the planet's structural strength, tearing it apart in a process called spaghettification, a technical term that's both accurate and darkly whimsical. Given all of this, you'd expect pulsars to be barren, lifeless, surrounded by nothing but radiation and empty space. And for decades, that's exactly what astronomers believed. Pulsars were fascinating objects to study, but they were solitary remnants of stellar death, interesting in their own right, but not places where you'd expect to find planets. Then, in the early 90s, astronomers discovered the first planets around a pulsar. It was a shocking finding. A pulsar designated PSR J2322-2650, located a couple thousand light-years from Earth, had not just one but 3 planets orbiting it. The discovery was confirmed through precise timing measurements by watching how the pulsar's pulses arrived at Earth and detecting tiny variations caused by the gravitational pull of the planets. It was an ingenious method, and it proved beyond doubt that planets could exist around pulsars. But these weren't normal planets. They were small, likely rocky, and they had probably formed from the debris of the supernova itself. They weren't survivors from before the explosion, they were second-generation worlds, born in the aftermath of stellar death, and they orbited at relatively safe distances, far enough from the pulsar that the radiation and tidal forces were survivable. They were strange, harsh worlds, but they made sense within the framework of what we knew about pulsar environments. What didn't make sense was finding a planet like the one around PSR J2322 A massive planet, orbiting incredibly close, deformed by tidal forces and yet somehow still intact. This wasn't a small rocky world formed from supernova debris. This was a giant, a world comparable in size to Jupiter, existing in an environment where giants shouldn't be able to survive. It was like discovering a delicate glass sculpture sitting in the middle of a blast furnace. The contrast between the fragility of the object and the hostility of the environment was jarring. And it raises profound questions. How many other pulsar planets are out there? Are we only seeing the ones that orbit close enough and are massive enough to detect, while countless others remain hidden? Could there be entire systems of planets around some pulsars, strange menageries of worlds forged in the aftermath of stellar explosions? And what does this tell us about the resilience of planets in general? We tend to think of planets as fragile, delicate things that require just the right conditions to form and survive. But maybe that's wrong. Maybe planets are tougher than we thought. Maybe they can endure conditions we assumed were fatal. Maybe the universe is full of worlds existing in environments we never thought to look for them in. The pulsar itself, PSR J2322-2650, is a millisecond pulsar, a particularly fast-spinning variety. It completes a rotation in just a few milliseconds, which places it among the fastest spinning objects known in the universe. The speed is thought to be the result of mass transfer from a companion star at some point in the past, a process that spun the pulsar up to its current rate. And that history might be key to understanding the planet. If there was a companion star, and if that star contributed material to the pulsar, perhaps it also played a role in the planet's formation or survival. Perhaps the planet is what's left of that companion, stripped and transformed by the intense environment. But even that explanation has gaps. Companion stars in binary systems are typically larger and more massive than planets. Stripping one down to planetary size would require processes we don't fully understand. It's possible, but it requires specific conditions and a sequence of events that we can only speculate about. The truth is, we're still piecing together the story. We have fragments, the discovery, the measurements, the theories, but the full narrative remains elusive. What we do know is that this planet is a survivor. It exists in a realm that should be lethal, and yet it endures. That resilience is one of the most compelling aspects of the discovery. It suggests that planets, as a category, are more robust, more adaptable, more capable of existing in extreme environments than we ever imagined. And that has implications far beyond this one system. It means that as we search for planets around other stars, we need to expand our thinking. We need to look in places we might have dismissed as too hostile, too unlikely. Because if a planet can survive around a pulsar, where else might they be hiding? Now, given everything we've discussed about how impossible this planet is, how hostile its environment is, you might be wondering, how did we even find it? That's where the James Webb Space Telescope enters the story, and its role in this discovery is as impressive as the planet itself. The James Webb Space Telescope isn't just another telescope, it's the culmination of decades of planning, engineering, and international collaboration. Launched after years of delays and cost overruns, it represents humanity's most ambitious attempt to peer into the distant universe and uncover secrets that previous instruments couldn't reach. With a mirror over 20 feet across, coated in gold to reflect infrared light, and positioned nearly 1 million miles from Earth at a gravitationally stable point called Lagrange Point 2, Webb is designed to see farther, deeper, and with greater clarity than anything before it. Infrared observation is Webb's specialty. While visible light gets absorbed or scattered by dust and gas in space, infrared light passes through more easily. This allows Webb to see through clouds of material that would be opaque to telescopes like Hubble. It can observe the first galaxies that formed after the Big Bang, hidden behind veils of cosmic dust. It can analyze the atmospheres of distant planets, detecting the chemical signatures of gases that might indicate habitability or even life. And it can study objects in our own galaxy with unprecedented detail, revealing structures and processes that were invisible to earlier instruments. But detecting a planet around a pulsar is a different challenge altogether. Planets don't produce their own light. They only reflect the light of their parent star, or in this case, the faint glow from the pulsar itself. And pulsars, despite their intense radiation, aren't very bright in visible or infrared wavelengths. They're most prominent in radio waves and X-rays. So finding a planet around a pulsar requires indirect methods looking for gravitational effects, measuring timing variations in the pulsar's pulses, or detecting the faint infrared signature of the planet itself, as it absorbs and re-emits heat. That's what Webb did. By observing PSR J2322-2650 in infrared wavelengths, the telescope detected the thermal emission from the planet. The planet, heated by radiation from the pulsar and possibly by internal tidal heating, glows faintly in the infrared. It's not a bright glow, nothing like the sun or even a distant star, but it's enough for Webb's sensitive instruments to pick up, and once detected, the signal could be analysed. Scientists could measure the planet's size, estimate its mass from orbital dynamics, and infer details about its composition from the wavelengths of light it emits. The data came through as a series of spectrographs showing how much light the planet emits at different wavelengths. Each wavelength corresponds to a different energy level, and different molecules absorb and emit light at characteristic wavelengths. By studying the spectra, scientists could identify which elements and compounds are present in the planet's atmosphere. Carbon compounds showed up strongly, suggesting the soot-filled atmosphere I described earlier. The overall pattern matched predictions for a carbon-rich world, supporting the diamond core hypothesis. But the real breakthrough was simply confirming the planet's existence with such clarity. Previous observations had hinted at something around the pulsar, but the data was ambiguous. Radio telescopes detected timing variations in the pulsar's pulses, suggesting gravitational influences from an orbiting body. But timing variations can have other causes: wobbles in the pulsar's rotation, interactions with the interstellar medium, instrumental artifacts. Confirming that a planet was actually there required direct observation, and that's what Webb provided. It saw the planet, it measured its properties, it removed any doubt. The researchers at the University of Chicago who led the study were using Webb as part of a broader survey of pulsar systems. They weren't specifically looking for this planet. It emerged from careful analysis of the data, a case of pointing the telescope at an interesting target and finding something unexpected. And that's often how breakthroughs happen in science. You design an instrument to answer certain questions, but along the way, it reveals things you never thought to look for. Webb was built to study distant galaxies and exoplanet atmospheres, but it's also proving invaluable for exploring exotic objects in our own galaxy, like this pulsar planet. The discovery was published in the Astrophysical Journal, one of the most prestigious and rigorous scientific publications in astronomy. Before a paper gets published there, it goes through peer reviewer process where other experts in the field scrutinize the data, the methodology, and the conclusions to ensure everything is sound. The fact that this discovery passed peer review and was published means the scientific community has examined it carefully and found it credible. It's not speculation or wishful thinking, it's solid, verified science. And the implications go beyond this one planet. Webb's ability to detect and analyze pulsar planets opens up an entirely new area of research. For years, pulsar planets were considered rare curiosities, interesting but not particularly important. Now, with Webb's capabilities, we can start systematically studying them. We can search for more planets around other pulsars. We can compare their properties, look for patterns, try to understand how they form and evolve. This single discovery might be the beginning of a whole new subfield of planetary science. What's particularly exciting is that Webb is still early in its mission. It's been operational for only a short time compared to the decades-long missions of telescopes like Hubble. There are years, potentially decades, of observations ahead. Every time Webb points its mirrors at a new target, there's a chance it will find something surprising. Another impossible planet, a galaxy that challenges cosmological models, an atmosphere on a distant world with chemical signatures we can't explain. The universe is full of mysteries, and Webb is the tool we've built to uncover them. The engineers and scientists who designed Webb couldn't have predicted this specific discovery. They built the telescope with general capabilities infrared sensitivity, high resolution, stable positioning, and trusted that those capabilities would lead to important findings. And they were right. The investment, the years of work, the technical challenges overcome, all of it is paying off in discoveries that expand our understanding of the cosmos. There's also something deeply human about this achievement. For most of history, humans could only wonder about what existed beyond our immediate surroundings. The stars were distant, unreachable, mysterious. We told stories about them, created myths, tried to make sense of the patterns we saw. Then, a few centuries ago, we built telescopes and began to see the universe as it really is: vast, ancient, filled with objects stranger than any myth. And now, with instruments like Webb, we're pushing that exploration even further. We're not just seeing distant stars, we're analysing their planets, studying their atmospheres, uncovering the details of worlds light years away. This pulsar planet, this lemon-shaped, diamond-filled world orbiting a dead star, is one of those details. It's a single data point in the vast catalogue of cosmic phenomena, but it's a significant data point, one that challenges our theories and expands our sense of what's possible. And it's a reminder that no matter how much we learn, the universe always has more to teach us. The researchers who made this discovery are still studying the planet, analysing additional data, refining their models. They're planning follow-up observations, possibly with other telescopes, to gather more information. They want to understand the atmosphere in greater detail, measure the planet's density more precisely, and perhaps even detect changes in the planet's shape or orbit over time. Each new piece of information brings them closer to answering the central question: how does this planet exist? But even as they work toward that answer, the discovery has already had an impact. It's sparked conversations across the scientific community. It's inspired new research proposals, new simulations, new ways of thinking about planetary formation and survival. And it's captured the public imagination, bringing attention to the wonders of astronomy and the power of modern technology to reveal those wonders. So what does all of this mean for our broader understanding of the universe? What are the implications of finding a planet that challenges our models? That's the question we need to explore next. Because this discovery isn't just about one strange world, it's about what that world tells us about the cosmos as a whole. Every major discovery in science has ripple effects. It's never just about the immediate finding, it's about how that finding changes the way we think, the questions we ask, the assumptions we reconsider. When Copernicus proposed that the Earth orbits the Sun, it wasn't just a revision of astronomical models, it was a fundamental shift in humanity's place in the universe. When Einstein published his theories of relativity, he didn't just correct Newton's laws, he transformed our understanding of space, time, and gravity. And when we discover a planet that breaks the rules we thought governed planetary formation and survival, we're forced to expand our framework, to admit that the universe is more complex, more diverse, more surprising than we realized. The lemon-shaped planet orbiting PSR J2322-2650 is that kind of discovery. It's not just a curiosity, a strange anomaly to catalogue and move on from. It's a challenge to our existing theories, and challenges are how science progresses. When your model predicts that something can't happen, and then you observe it happening anyway, you have to update your model. You have to figure out what you got wrong, what you missed, what new processes or mechanisms you need to include to account for the observation. So what specifically does this planet challenge? Let's start with planetary formation theory. We have a fairly well-established understanding of how planets form around normal stars. A cloud of gas and dust collapses under its own gravity to form a star. The leftover material swirls around the star in a disk, a protoplanetary disk. Over time, particles in the disk collide and stick together, gradually building up larger and larger objects. Small dust grains become pebbles. Pebbles become boulders. Boulders become planetesimals, objects miles across. Planetesimals collide and merge, forming protoplanets, and eventually, over millions of years, you get a system of fully formed planets. This process is well supported by observations. We see protoplanetary disks around young stars. We see debris disks around older stars, evidence that planet formation has occurred. We can run computer simulations that reproduce the general structure of solar systems like our own. The theory works, but it's a theory for planet formation around normal stars, stars that are alive and burning fuel through nuclear fusion. It's not a theory for planet formation around dead stars, around pulsars born in violent explosions. Pulsars don't have the same kind of protoplanetary disks. When a massive star explodes in a supernova, it ejects most of its outer layers into space. The material doesn't settle into a nice orderly disk. It flies outward at tremendous speeds, dispersing into the surrounding interstellar medium. Some material might remain bound to the neutron star, perhaps forming a debris disk of sorts, but it's not the same environment as a protoplanetary disk around a young star. The temperature, the composition, the dynamics all are different, and yet somehow planets do form around pulsars. We've seen it with the planets around PSR B1257+12, and now with this new discovery. So either our theory of planet formation is incomplete, or there's a different process at work around pulsars. Maybe planets can coalesce from supernova debris more readily than we thought. Maybe the conditions, while extreme, are actually conducive to rapid planet formation under certain circumstances. Or maybe these planets aren't forming around the pulsar at all. Maybe they're being captured, rogue planets wandering through space that happen to be ensnared by the pulsar's gravity. Each possibility has profound implications for how common planets are in the galaxy, where they can form, and what diversity of planetary environments exists. Then there's the question of survival. Even if we accept that planets can form or be captured by pulsars, how do they survive the harsh conditions? The radiation should erode them. The tidal forces should tear them apart. The lack of a stable energy source should mean they're frozen, lifeless husks. But this planet isn't just surviving, it's maintaining a thick atmosphere, retaining its structure, and existing in a stable orbit. What's protecting it? One possibility is that the planet is simply massive enough. More massive objects have stronger self-gravity, which helps them hold together against tidal forces. A Jupiter-sized planet has far more internal cohesion than a small rocky world. Perhaps there's a threshold, a minimum mass, below which pulsar planets can't survive, but above which they're stable. If that's true, it would explain why we don't see lots of small planets around pulsars, only the giants make it. Another possibility is that the diamond core plays a role. Diamonds are incredibly strong. A core made of diamond would be more rigid than a core made of molten metal or compressed hydrogen. That rigidity might help the planet resist tidal deformation, keeping it from being torn apart. It's speculative, but it's the kind of hypothesis that can be tested with simulations and further observations. There's also the question of atmosphere retention. Pulsar radiation should strip away atmospheres over time, especially if the planet is close to the pulsar. But if the planet is constantly replenishing its atmosphere, perhaps through volcanic outgassing, or through chemical reactions in its interior, it could maintain a thick atmospheric shield despite the radiation. The carbon-rich atmosphere might even be particularly good at absorbing certain types of radiation, protecting the planet's interior. Again, these are hypotheses. We need more data to confirm or refute them, but they're the kinds of ideas scientists are exploring now that we know this planet exists. Beyond the specifics of this one planet, the discovery has broader implications for exoplanet science. We've discovered thousands of exoplanets around normal stars. We've found hot Jupiters, super-Earths, ice giants, rocky worlds in habitable zones. We've catalogued an incredible diversity of planetary systems. But we've barely scratched the surface of extreme environments. Pulsar planets are just one category. There might be planets around white dwarfs, or around binary star systems with unusual dynamics, or in the outskirts of galaxies where conditions are very different from our neighbourhood. Each of these environments might harbour planets with properties we haven't seen before. And if planets can exist in such a wide variety of environments, what does that say about the potential for life? We tend to focus our search for life on planets that resemble Earth-rocky worlds in the habitable zones of sun-like stars. That's a reasonable place to start, because that's the environment we know can support life. But if planets are more diverse, more resilient, more capable of existing in extreme conditions than we thought, maybe life is too. Maybe there are forms of life adapted to high radiation environments, or to planets with diamond cores, or to worlds orbiting dead stars. Maybe the universe is teeming with life in places we never thought to look. This is speculative, of course. We have no evidence of life on pulsar planets. The conditions are extraordinarily harsh, and it's hard to imagine how life as we understand it could survive there. But life has surprised us before. Every time we've discovered life on Earth in an environment we thought was uninhabitable, deep ocean vents, acidic lakes, frozen Antarctic rocks, we've had to revise our assumptions. Maybe the universe will surprise us in the same way. The discovery also highlights the importance of continued investment in space telescopes and observational astronomy. Webb is expensive. The mission cost billions of dollars and took decades to develop. But discoveries like this demonstrate why that investment matters. We're not just taking pretty pictures of distant galaxies. We're uncovering fundamental truths about the universe, challenging our theories, expanding human knowledge. And that knowledge has value beyond the immediate scientific findings. It inspires future generations of scientists, engineers, and explorers. It gives us perspective on our place in the cosmos. It reminds us that the universe is vast, ancient, and full of wonders we're only beginning to understand. So what comes next? The researchers who made this discovery aren't finished. They're planning follow-up observations with Webb and possibly other telescopes. They want to study the planet's atmosphere in more detail, looking for specific molecules and compounds that can tell them more about its composition and history. They want to measure the planet's orbit with greater precision, looking for variations that might indicate the presence of other planets in the system. They want to understand the pulsar itself, its rotation rate, its magnetic field, its history, to see how it might have influenced the planet's formation or survival. And beyond this one system, astronomers are searching for more pulsar planets. Now that we know they can exist in such extreme conditions, it makes sense to look for others. Are there more lemon-shaped worlds out there? Are there pulsar planets with different compositions, different shapes, different orbits? How common are they? And what can the population of pulsar planets as a whole tell us about planetary science? These are questions that will take years, maybe decades, to answer fully, but that's how science works. Each discovery raises new questions. Each answer opens new lines of inquiry. We're not building towards some final, complete understanding of the universe we're engaged in. An ongoing process of exploration, learning, and refinement. And that process is one of the most deeply human endeavors we undertake. It's an expression of our curiosity, our desire to understand, our refusal to accept ignorance when knowledge is within reach. As we stand on the edge of this new understanding, as we grapple with the implications of a planet that challenges our models, we're reminded once again that the universe is stranger, richer, and more wonderful than we ever imagined. And that sense of wonder, that feeling of awe in the face of cosmic mysteries, is something worth preserving. Which brings us to the final question. What does this all mean for us, here on Earth, looking up at the stars and pondering our place in the universe? There's a certain feeling you get when you first learn about something that challenges everything you thought you knew. It's a mixture of excitement, confusion, and awe. Your mind races to integrate the new information, to fit it into your existing understanding. Sometimes the new information fits easily, just expanding what you already know. But other times, it doesn't fit at all. It contradicts your assumptions. It violates rules you thought were unbreakable. And in those moments, you experience a kind of cognitive vertigo, a sensation that the ground beneath your understanding has shifted. That's what this discovery offers, a lemon-shaped planet with a diamond core, orbiting a dead star so fast that years pass in hours, existing in an environment that should have destroyed it long ago. It's not just a new piece of information to add to the catalogue of known planets. It's a revelation that forces us to reconsider what we thought we knew about how planets work, where they can exist, and what forms they can take. For the scientists who study these things professionally, the discovery is both thrilling and humbling. Thrilling because it's exactly the kind of finding they dream about, something unexpected, something that opens new avenues of research, something that will be remembered and cited for years to come. Humbling because it's a reminder that no matter how sophisticated our theories become, no matter how many observations we accumulate, the universe still has the capacity to surprise us. We build models, we make predictions, we think we understand the rules, and then nature shows us something we never predicted, and we realize how much we still have to learn. But this discovery isn't just for scientists. It's for anyone who's ever looked up at the night sky and wondered what's out there. It's for anyone who's felt that sense of curiosity about the cosmos, that desire to understand the universe beyond our small corner of space. Because what this discovery tells us more than anything else is that the universe is far stranger and more diverse than we ever imagined. And that means there's still so much to explore, so much to discover, so many mysteries waiting to be uncovered. Think about what we've learned just from this one planet. We've learned that planets can survive around pulsars, even when they shouldn't. We've learned that tidal forces can deform entire worlds into shapes we've never seen before. We've learned that diamond cores might exist on a scale that dwarfs anything on Earth. We've learned that our theories of planetary formation need to be expanded, revised, made more flexible to account for environments we didn't think were hospitable to planets. All of that from one world, orbiting one dead star, detected by one telescope. And Webb is just getting started. The James Webb Space Telescope has years of observations ahead of it. Every week it's pointing its mirrors at new targets, gathering data, revealing details of the universe that were hidden before. Some of those observations will confirm what we already know, filling in details and refining our understanding. But some, like this pulsar planet, will surprise us. They'll show us things we didn't expect, things that challenge our assumptions, things that expand the boundaries of what we thought was possible. What might those future discoveries look like? We can speculate, but we can't know for sure. Maybe Webb will find more pulsar planets, revealing that they're more common than we thought. Maybe it will detect atmospheric biosignatures on an exoplanet, giving us the first hint that life exists beyond Earth. Maybe it will observe the formation of planets in real time, watching as dust and gas coalesce into worlds around young stars. Maybe it will see galaxies so distant and ancient that they formed shortly after the Big Bang, showing us what the universe looked like in its infancy. Each of these discoveries would be transformative in its own way. But beyond the specific findings, there's something deeper at work here. There's a process, scientific exploration that represents one of humanity's greatest achievements. We're a species that evolved on a single planet, in a single solar system, in one small corner of one galaxy among billions. For most of our history, we knew nothing beyond our immediate surroundings. The sky was a mystery, the stars unreachable, the cosmos incomprehensible. But over centuries, through observation, experimentation, and reason, we've gradually expanded our understanding. We've mapped the solar system, discovered other galaxies, detected planets around distant stars, and even begun to understand the origin and fate of the universe itself. And we've done it without ever leaving our planet, except for a few brief visits to the moon. We've done it with telescopes, with mathematics, with instruments that detect light from across the cosmos. We've done it by asking questions, testing hypotheses, building theories, and being willing to revise those theories when new evidence emerges. It's a testament to human ingenuity, curiosity, and perseverance. This pulsar planet is part of that larger story. It's one more chapter in the ongoing narrative of human exploration and discovery. And like all the best chapters, it raises as many questions as it answers. How did this planet form? How has it survived? Are there others like it? What does it tell us about the diversity of worlds in the universe? What might we find next? We don't have all the answers yet. We might not have them for years. But that's okay. The journey of discovery is as valuable as the destination. Every question we answer opens up new questions. Every mystery we solve reveals deeper mysteries. And that process, that endless cycle of inquiry and discovery, is what keeps science vibrant, exciting, and profoundly human. For those of you watching this, I hope this story has sparked something in you. Maybe it's curiosity about astronomy. Maybe it's appreciation for the scientists and engineers who make these discoveries possible. Maybe it's simply a sense of wonder at the strangeness and beauty of the universe we inhabit. Whatever it is, hold on to it. Because that sense of wonder is precious. It's what drives us to explore, to learn, to push beyond the boundaries of what we know. And we're living in an extraordinary time for exploration. We have telescopes that can peer across billions of light years. We have spacecraft visiting distant worlds in our own solar system. We have instruments that can detect gravitational waves, neutrinos, and particles from the edge of the universe. We're asking questions that previous generations could only dream about, and we're finding answers that exceed even the wildest speculations of science fiction. This planet, this impossible, lemon-shaped, diamond-filled world is a symbol of that age of discovery. It's a reminder that the universe doesn't play by the rules we write in textbooks. It's more creative, more inventive, more surprising than we give it credit for. And every time we think we've got it figured out, it shows us something new. So what comes next? More observations, certainly. More analysis, more theories, more debates among scientists about how to explain what we're seeing. But also more discoveries, more planets, more stars, more galaxies, more mysteries uncovered, more questions asked. The universe is vast and we've only just begun to explore it. If this journey through the cosmos fascinates you, if the idea of diamond planets and dead stars and impossible orbits captures your imagination, then stay with this community. Hit that subscribe button because we're going to continue exploring these discoveries together. Drop a comment below and let me know what aspect of this planet amazes you the most. Is it the shape, the diamonds, the speed of its orbit, or something else entirely? And hit that like button if you want to see more deep dives into the mysteries of space, because this is just the beginning. Webb is out there right now gathering light from distant corners of the universe. Other telescopes are scanning the skies, missions are being planned, and somewhere, in some dataset waiting to be analysed, there's another discovery just as surprising as this one, another world that breaks the rules. Another cosmic mystery that will challenge our understanding and expand our sense of what's possible. The universe keeps surprising us, and as long as we keep looking, as long as we keep asking questions, as long as we maintain that sense of wonder and curiosity, it will continue to reveal its secrets, one impossible planet at a time.